You type a question into a box, you hit enter. A few seconds later, something types back. It sounds human, it reasons like human, it writes like human, and you have absolutely no idea what just happened inside that machine. Most people assume there is some giant database of answers sitting on a server somewhere, waiting to be looked up. There isn't. Others assume ChatGPT thinks the way you think, with something like awareness or intention driving every word. It doesn't. What actually happens between the moment you press enter and the moment the first letter appears on your screen is stranger, more mechanical, and more fascinating than either of those explanations. It is also, once you understand it, one of the most counterintuitive engineering achievements in the history of computing. To understand it, you need to go back to a problem that had been quietly frustrating computer scientists for decades. How do you teach a machine to understand language? Early attempts were rule-based. Researchers tried writing down every grammatical rule they could think of, encoding logic like a giant flowchart. If the sentence contains a noun followed by a verb followed by an object, interpret it this way. If the word appears in this context, assign it this meaning. It was painstaking work and it failed almost immediately in practice. Language is too messy, too contextual, too dependent on things that aren't said. The word bank means something completely different in the sentence about a river than it does in the sentence about a loan, and no fixed rule can reliably tell a computer which is which without understanding the entire sentence around it. The breakthrough came not from writing better rules, it came from giving up on rules entirely. In 2017, a team of researchers at Google published a paper called "Attention is All You Need." The 8 authors, including Ashish Vaswani and Jakob Uskorit, described an entirely new kind of neural network architecture they called a transformer. The transformer did not try to process language word by word in a fixed left-to-right sequence the way earlier systems did. Instead, it processed every word in a sentence simultaneously, and it measured the relationship between every single word and every other word in the sentence at the same time. This mechanism, which the team called self-attention, allowed the model to understand context in a way no previous architecture had managed. The word bank near the word river pulls the meaning in one direction. The word bank near the word savings pulls it in another. The transformer learned to feel those pulls dynamically across an entire sentence in a single pass. That paper is the direct ancestor of every large language model you have ever used. ChatGPT runs on a transformer, so does every model built after 2017 that you have heard of. That single research document, quietly uploaded to a preprint server, restructured an entire field. But the transformer architecture is only the skeleton. The intelligence, such as it is, comes from the training. OpenAI trained the model behind ChatGPT on an almost incomprehensible volume of text. Books, websites, articles, forums, academic papers, code, hundreds of billions of words, scraped from across the internet and digitized libraries, fed into the network as raw input. During training, the model performed one task over and over and over again, billions of times. Given this sequence of words, predict the next one. That's it. That is the entire training objective. No human wrote out correct answers. No one labeled the text with explanations. The model simply saw a sentence with the last word hidden, made a prediction, compared its prediction to the actual word, measured how wrong it was, and adjusted the weights inside its billions of internal parameters slightly to be less wrong next time. This process, called gradient descent, is how the model learns, not by memorizing facts, not by storing answers, by adjusting billions of tiny numerical dials called weights across a network of interconnected layers until the pattern of those adjustments encodes something that functions like an understanding of language structure, tone, logic, and context. Think of it like this. Imagine you handed someone a billion human conversations, told them to read every single one, and told them their only job was to get better at guessing what word came next. After long enough, that person would absorb something deep about how sentences are constructed, how arguments flow, how questions imply certain kinds of answers, how tone shifts when the subject changes. They wouldn't have memorized every conversation, they would have internalized the shape of language itself. That is what gradient descent does to a transformer. Over trillions of prediction attempts, the weights in the network stop being random numbers and start being a compressed, encoded map of how human language works. The final model has roughly 175 billion of these parameters in the version released as GPT-3, the foundation beneath early ChatGPT. Each parameter is a floating point number, a tiny decimal value holding no meaning on its own. But together, the entire web of those numbers, shaped by training on hundreds of billions of human-written words, produces something that can write a poem, debug code, explain a legal contract, and hold a conversation that feels startlingly real. Now here is the part that surprises almost everyone when they first hear it. ChatGPT does not retrieve answers. It generates them. Every single word in every response is chosen one at a time, in sequence, by calculating a probability distribution across the entire vocabulary and sampling from it. The model looks at everything written so far, your question and its own previous words, runs it through all those layers of attention and computation, and produces a list of possible next words ranked by probability. The most likely word is not always chosen. There is a sampling temperature, a dial that controls how much randomness is introduced at each step. Turn the temperature down and the model becomes more predictable, more conservative. Turn it up and it becomes more creative, occasionally more wrong. The word that appears on your screen is not retrieved. It is, in the most literal sense, predicted into existence. There is one more mechanical detail worth pausing on because it changes how you picture the whole process. ChatGPT does not actually operate on words, it operates on tokens. A token is a chunk of text, sometimes a full word, sometimes just a few letters, sometimes a punctuation mark on its own. The word unbelievable might be split into 3 tokens. A common short word like the is a single token. The model never sees your sentence as you wrote it. It sees a sequence of numbered tokens, each one converted into a high-dimensional vector, a list of hundreds of numbers that encodes the token's position in a vast mathematical space alongside every other token it has ever encountered. That vector is what flows through all those layers of attention and computation. Language, reduced to coordinates in a space too large for any human to visualize, being transformed by matrix multiplications into new coordinates, and then decoded back into the next token of text on your screen. The gap between what you experience and what the machine is actually doing could not be wider. This is why ChatGPT sometimes makes things up. Researchers call this hallucination, a word that was borrowed by Yann LeCun, a Turing Award-winning AI researcher at Meta, and others in the field to describe confident outputs that are factually wrong. Because the model is not looking anything up, it has no mechanism to check whether a generated sentence is true. It only knows whether the sentence sounds like the kind of thing that would appear in its training data. A plausible-sounding wrong answer and a plausible-sounding right answer are generated by exactly the same process. The model cannot feel the difference. You have to. After the base model is trained on raw prediction, there is a second stage that shapes it into something you can actually have a conversation with. OpenAI used a technique called reinforcement learning from human feedback. Human raters looked at pairs of model responses and marked which one was better, more helpful, more accurate, less harmful. Those preferences were used to train a separate reward model, and that reward model was then used to fine-tune the language model further, nudging it toward responses that humans preferred. This is the process that turned a raw next-word prediction engine into something that says please and thank you, admits uncertainty, declines certain requests, and explains its reasoning step by step. Ilya Sutskever, one of the co-founders of OpenAI, has described this stage as the difference between giving a model knowledge and giving it values. The base model learns what humans say. The fine-tuning stage shapes how it says it and which things it chooses not to say at all. All of this runs on hardware you almost certainly cannot picture. The training of a model like GPT-4 requires thousands of specialized graphics processing units running in parallel, coordinated across data centers, consuming enough electricity to power a small city. A single training run can cost over $100 million. The inference, the computation that happens every time you send a message and wait for a response, is cheaper but still substantial. Running across clusters of chips designed specifically to perform the matrix multiplications that transformers require at speeds that would have seemed impossible to the researchers writing those early rule-based language systems in the 1980s. You don't see any of that. You see a blinking cursor and then words.
Here is the most important thing to hold on to when you think about what ChatGPT actually is. It does not know anything in the way that you know things. It has no memory between conversations unless one is given to it. It has no access to the internet unless a tool is connected. It has no goals, no preferences, no experience of the world beyond the statistical patterns learned from text. When it tells you it understands something, that is itself a predicted output, a sequence of words that followed naturally from what came before, not a report from an inner mental state. And yet, the outputs are often useful, often accurate, and sometimes genuinely surprising in their coherence and depth. Not because something is home inside the model, but because the patterns of human thought, encoded in billions of words written by billions of people across centuries of recorded language, are themselves extraordinarily rich. When the model predicts the next word well enough, across enough turns of a conversation, something that looks a great deal like intelligence emerges from the bottom up. You typed a question into a box. What typed back was not a mind. It was a mirror made of mathematics, trained on everything humanity has written down, reflecting your question back at you in the shape of an answer. Whether that answer is the one you needed, only you can judge. But the mechanism that produced it, that chain of predictions, probabilities, and parameters running silently in a data center you will never see, is one of the most intricate things humans have ever built. And it all began with one deceptively simple question. Given everything that came before, what word comes next?